Let's welcome our speakers of our very first talk in the afternoon. So Tim has been working on a lot of the infrastructure for Julia, debugging and increasing the latency of a lot of parts of the ecosystem. And then
My main job.
Claire has been doing some strides in terms of the internals, moving the parser into Julia itself, and doing a lot of internal work that makes things easier for people that want to come into working in the core parts of the language. So let's welcome them and let's hear what they have to say.
Thank you.
Thank you. Hello, everyone. OK, so I titled this talk, Dude, Where's My Code? Because sometimes it feels a bit like this diagram on the right-hand side here. The compiler reads a bit of the code, and then it kind of forgets where things were. So it'll say, oh, there was an error. It probably started, it was in the expression starting on line 10. And then the actual line that the error is on is line 15, because the expression is long, something like that. OK. Oh, and the official title, the non-joke title, Improving Julia's Usability with Code Provenance. So what's code provenance? Provenance is just the place of origin, the earliest known history of something. And code provenance is knowing where in your source code a piece of code came. Well, when the compiler is processing your source code, it'll have some internal data structures, and having your source code attached, a location in your source code attached to those internal data structures at all times, so it can always point at a particular location. So in this example here, we might have a syntax tree data structure, and we're digging into the internal list of children of that syntax data structure, and we can go back to the code and print it out. These are the bytes you're looking for. It's right these ones here. Right, and what we'd like to do, there's this diagram here of the rough kind of list of passes that code goes through in the compiler. I don't know much about this side of it, but this is where I'm working up here. And we'd like to keep that information all the way through. So if we can get it all the way to the end, we can have this kind of provenance information, like this isod or whatever, being known about in stack traces, for instance. But it's a long way to get all the way to the end. So we're just in the lowering part at the moment. Right, so I've been working on this kind of thing for a little while now. This is the PR which got Julia's syntax.jl into base. And so that's now in 1.10. So that's the first part of this chain of things. Now I'm working on lowering, so a little bit of history there. Back in apparently 2019, I decided it was a good idea to start to rewrite lowering for fun, for no other reason, I don't think. So that was back in Julia 1.1 days. And Tim made this julep earlier than when I started working on it, which I didn't know about, and asked for code provenance, which I didn't know about. So it's lucky that I didn't finish this pull request, because it didn't have any better code provenance than what the existing parser and lowering had. So anyway, one thing that's notable about this julep that Tim wrote, there wasn't a lot of discussion, but it's a bit telling the number of issues that eventually ended up linking to that. And there's a lot more, actually, that should have linked to that, but nobody really knew about it, I don't think. So there's probably, I don't know, 50 or so issues, it would be my guess, that should kind of have been linked to that. OK. Right, so I've got a new package called Julia Lowering, where I'm rewriting the lowering passes. So lowering is symbolic simplification. You have these so you have a syntax tree and from the parser, and you'd like to simplify the forms, the syntactic forms that you have, to a very small number of syntactic forms. That's really distracting, the drone. Sorry. OK, so we're going to show a bunch of cases where better provenance information is going to lead to better things, about better user experience, I guess. So one example here is this is the existing error you get if you do this kind of thing. So what's wrong here is someone has double interpolated this x here. This should just be x, not $x. But it doesn't really say, like, what it does say is that this is on line 2. Now, that's correct. And it does say it's involving in dollars, but there's a few dollars there. So it's not probably very obvious if you've accidentally done this, like, what is the actual problem? So this is the existing implementation of Julia Luring, which is very incomplete at this stage, but it does deal with this problem. Just kind of ignore the include string thing there. That's just to do with, and in following examples, it's just to do with, I haven't connected this up to the REPL or anything, because it's all very incomplete, and I wouldn't be able to use the REPL. So just focus on, like, that's the source code, the same as before. In this case, it says, there's the problem. That's what you should fix. OK, so another example of this kind of thing. So that the previous one's an example of a built-in compiler pass that you can kind of think of user macros as custom compiler, custom lowering pass that happens before the rest of lowering. So I've implemented call in the new with the new lowering data structures, and just to give an example here. So the previous error that you would get was actually pretty good. It said what the argument was, some number. So someone's tried to call the C function printf, and they forgot to say what the types were, the C types of these things. So the new system will still say, though, like, here it is. It'll show you your source code, not some reconstruction of that source code. It'll show you your source code, and it'll underline the location within your source code. Another example, which is probably a little bit showing a little bit more detail about, like, in this case, existing SQL doesn't have any syntax that it can use to demonstrate where the issue is, so it can't really print anything useful. The problem is that the cint, colon cint is forgotten off the end of here. And so in this case, it'll say, well, here it was. You forgot it here. I wouldn't say that the error message there is the best thing, but we can work on that. It knows at least where the issue was. Yeah, so this is like user-written macros can emit precise syntax errors, basically, for their custom syntax that they're supporting. OK, so over to Tim for the next.
All right. So one of the things I want to emphasize in this is that in the work that's being done currently to fix code provenance, I am playing no role. Claire is doing 100% of the heavy lifting. My role here is as a wannabe user. Think of me as the evangelical preacher, the motivational speaker, who's telling you that all of you will get ponies if we can only fix this one issue. And I think this is worth doing because all of the difficult issues involved in sort of keeping track of what happens at every transformation stage of our code pipeline are very detailed bookkeeping, and it may sound very abstract, but I really do believe that this may lead to concrete benefits. One of the things I want to point out is that none of these are promises that we can deliver these benefits, but I think one thing that is safe to say is that we probably can't deliver the benefits unless we fix this problem. OK? So one of the...
So to interrupt you, Tim, there's going to be a comment in the source about ponies.
Yeah.
There isn't yet, but
ponies, gotcha.
Yeah,
OK, very good.
You get ponies.
So one of the bits of tooling I'm going to give you 3 examples from my own experiences of working on Julia's tooling where I think this would make a big difference. So one of the places where I and many other people have contributed is in trying to bring information about types back in a more user-friendly way to programmers, both new and experienced alike. And so if you've not seen this before, this is a really nice package called Cthulhu. I'll do it on this little demonstration right here. All this is doing is taking 2 input arguments, and it's initializing an accumulator, and then it's adding them one by one. And I'm breaking it out in these different lines to sort of illustrate a few points, basically. And then so there's this absolutely lovely package, Cthulhu, and if you descend on it, and in this case, note that the x argument is going to receive an int, and the y is going to receive a float 64. And so if you look at this then interactively in your session, you'll see that this code has now been annotated in the following way. And what it's showing you is that even though the raw Julia source code isn't typed in any static way, it's showing you what the type of every object is as things propagate through the code base, right? So you know what the input argument types are. You can see that Z has a type of int at this stage of the program, but as soon as you add a float 64 to it, now Z changes to a float 64. That's not a problem. That's not a type instability. Julia's compiler is perfectly capable of handling it. That's why this is blue instead of red, for example. And then it gives you a return value of known type float 64. OK? So this is a case where this worked. Now, the thing that should be pretty obvious about this example is we're taking information that's computed at a deeper level of the compile chain, the type inference stage, and we're bringing it back to annotate the source code as the user wrote it, right? Now, we don't really have the tooling to do this. So this is actually a giant hack. It works surprisingly well, but it's very easy to break. And it breaks in real-world cases. I can't give you a real-world case that also fits on one screen very well. But here's a very simple example where I've broken it. I've just rewritten this. It's the exact same code. Julia's compiler generates the exact same machine code from this. It's just written in a different way. And if you pass this through Cthulhu, then what you get is this. So you can see that the type annotation works up to a point, and then it fails. Why does it fail? It fails because the way that we currently valiantly try to bring information back from the type inference stage up to the source code stage is based on 2 things: line numbers and pattern matching. And the problem is that in this case, we have the same pattern, z plus equals x, appear twice on the same line, and the types attached to the things are different in the 2 cases. So there's no really good way of reporting what's actually happening here, right? Now again, sometimes, this is very few people would write this code in this way, but this happens reasonably frequently in more complicated code bases. Not only does it not annotate some types, it also occasionally gets the types wrong. And so, yes, we could continue bashing on this and making it better in principle, but the right way to do it is just keep track of things as you go forward through the compiler pipeline, not try to make guesses based on pattern matching, working your way backwards. OK, here's another, again, speculative example about what we'll be able to make better. And this is, many of you probably know that Julia has a debugger. And again, this is something that I and many other people have worked on. And it does some nice things. At the last JuliaCon, I pointed out that there are some usability issues in Julia's debugger, though, that are associated with the fact that the debugger works on not the source code, but on the lowered code. And going back and pretending that it's operating on the source code causes some usability problems. Here I'm going to focus on a separate and more speculative issue. And that is that the other big complaint, and it's a very legitimate complaint about our debugger, is that it's really, really slow, right? So here I have a simple test code. It's just going to iterate over an array and sum all of the elements. I'm not putting in that much data into my array, although it's not all that trivial. And if you actually run this in compiled mode, it's 50 microseconds to actually execute this sum. However, if you run this very same code in Julia Interpreter, which is the foundation of our debugger, right, it takes almost 11 seconds to execute the same thing, right? So that's more than 5 orders of magnitude slower than compiled code, right? And so what that means in practice is the debugger is often not useful on the actual, say, problems that triggered the error you'd like to debug, right? You have to construct a small toy example that generates the same error, and then you can step into your code. This is also the motivation in part for other tools like Infiltrator or just print line debugging with Revise, right? So but there's a potential alternative way that we could maybe make things a little bit faster. And so for the purposes of this talk, in a couple hours, I hacked together an interpreter that works not at the level of Julia's lower code, but at a deeper level of the compilation, the IR code level. So this is after method, you type inference and method lookup and inlining have occurred. And if you run this in this little IR code interpreter, which you can see right here, the one problem with this IR code interpreter is that this is literally the only function in the universe this can probably run, right? Because I just built it for this one purpose. But you can see that it's more than 100-fold faster than our current debugger, right? Now, and in fact, we suspect that's not the end of it because there's one single bottleneck that's dominating the output of this, and that is boxing the outputs of Julia's intrinsics for the experts in the audience, basically. And so I think at least in principle, we could have a debugger that is vastly more useful if it were operating at a deeper level of the compile pipeline. The problem is we could write that interpreter today. The problem is it would be useless. And the reason why is that when you're running at that stage of the compiler pipeline, and now you say, oh, what is the value of X on line 37 of my code? We have to say, have no idea what's X. I just know about all these SSA values in my code, and I can't link them back to the actual named variables in my source code, right? So we really can't build a usable debugger that works at this level of Julia's code, but we could if we were able to keep track of where things came from through the stages of compilation. The final thing, a bit of tooling that I'll mention that I've worked on is Revise, and it may be curious that Revise is also affected by provenance. And the reasons why it is because it associates methods with source text. And having only line numbers as a means of identifying the source text is just grossly inadequate, right? One very obvious example of that is if you start editing a file and you just add a comment above some methods, it pushes them down in the file, and so at this point now the line numbers are completely inaccurate, right? But there are lots of other reasons why line numbers are inadequate as a source of provenance. And here's an example that, you know, it was only when Revise hit 3.0 that we were able to handle code like this. So there's a surprising amount of Julia code that gets defined kind of like this, right? And it's not wrong to say, for example, that this method is defined on this particular line here. But if you edit the text of the file and you say delete, you decide not to support float 16 anymore, then what Revise actually does now is it deletes the method for float 16, right? So that in your runtime, now you'd get a method error if you pass in a float 16, which is what you've decided you want, actually, right? And the problem is that without better code provenance, how is Revise supposed to know that the number of methods and the signatures of those methods that are defined in this line depend upon the line above that, right? And so the way that Revise solves this problem is insane, right? And so it actually re-implements the entire front end of Julia's parsing and lowering framework, basically. Or not the lowering framework, but what it does basically is it builds an interpreter on the lowered code, and it goes through the entire redefinition of the module up to the moment where it would define the method, and then it takes a quick sidestep and says, OK, now I know the signature, stash that, boom, done, basically, right? It's an insane design. It breaks with every single Julia release, and keeping the whole thing running is very, very tedious, right? So what would be really nice is to give Revise a sane design, and then much of Revise could move either into base Julia or a standard library. It wouldn't hopefully break with every release, and that basically involves, instead of redoing all the work that all the parsing and lowering stages have to do, just do it right the first time and keep track of the textual dependencies of every signature. OK, so those are the three examples I wanted to give.
Great, thanks, Tim. OK, so moving on. Oh, I think I've got a stray slide in here.
Don't worry, just.
Oh, OK. Yeah, no, OK. I don't know what happened there. OK, so what I'm going to do is talk about how does it actually work. So Julia lowering, so let's I'll show you a demo of Julia lowering, doing some lowering. Actually, just to talk about this slide slightly. So lowering itself, like I was saying that there's this parse system, the compiler does a whole bunch of passes. Lowering itself is actually a set of passes. So we're going to see that in a moment. I'm going to show you each pass for some example code. But yeah, the passes are listed here. There's macro expansion. There's desugaring, which is taking the complicated surface syntax forms like broadcast and all sorts of things, array comprehensions, various things, and turning them into basically very simple, much simpler syntactic forms like function calls. Then there's scope resolution. This resolves the identity of each name, so you find out which things are local, which things are globals, which things are arguments to functions. Closure conversion, that's not implemented yet in Julia lowering. That's a whole pile of code to write, so we're not going to look at that. IR generation, so the last stage of all of this is to take these syntax trees and turn them into a flattened set of statements, list of statements, which is the body of the methods and stuff which is defined. Okay. And through all of that, we're going to see that the provenance is, or we're going to have a look at the provenance information that we kind of keep track of. Okay, cool. So on the left-hand side here, I've got just a Julia source file, and I'm going to be looking at this piece of code here. So there's a let block here. So let's just look at, oh, OK, sorry. Keyboard shortcuts. This isn't my usual window manager. Try not to do that again. OK. OK, so let's look at this piece of source code. So the very first thing is to parse that source code. So that's this line here. Well, sorry, it's further up. These are the passes. You don't have to worry about these. But basically, what is happening in each of these is we're taking a previous syntax tree. So the very first thing was we parse. We parse the source code. We put it into the macro expansion pass, which is called expand forms 1. It does have a couple of things that aren't macro expansions, so that's why it's called that. This is the desugaring step. This is the scope resolution. We've got a linearization step, which is the IR code conversion. And then finally, there's support to convert to Julia's existing format so that we can actually run that code. All of these other ones are data structures, which are specific to Julia lowering, and they need to be because we need a place to put all this provenance information. OK. So, so the expression that we get from that piece of source code. Sorry. The expression we get from this piece of source code is this tree over here. And we're going to look at the desugared tree. So a let block introduces a new x here. So this x here is not this x here. So what we see that has had to happen is a temporary variable is needed to be introduced for the right-hand side of this. So it's this temp here. In fact, let's print that out. The desugared tree. So we'll print this back as Julia source code. So we've taken that let block, and we've created this temporary variable for the right-hand side. We've said that that's a local inside this scope block thing, which is internal concept in lowering. And then we just assign a new x, which is contained within the scope block, to the temporary. So this is like avoiding and confusing which x's are which. And then we print that's the body of this thing here. OK. So that is desugaring. So if we dig into this desugared expression, and we look for the second first element. So this is the assignment to this temporary variable. If we look at the first, OK, so the very first element of that is just a temporary variable. Now, this temporary variable just arises from the right-hand side of this, not the left-hand side. So let's show the provenance of that. OK, so that says it's in the source code there. And in fact, what's actually kept here is more information. It's the entire set of expression transformations that were done in order to get to this temporary variable, or the entire set of sort of the entire provenance tree, I guess you can say. This is not an interesting tree, but there are cases where this needs to be an actual tree, not just a linear link, like a linked list. OK, so I guess we'll also look at the scope resolution pass. Oh. OK. Let's show that this way. Copy it. So one of the things, oh goodness, let's just copy this. What have I done? Oh no, I see what I've done. Duh. OK, there we go. So the point I'm trying to show here is that so in scope resolution, the x's, so we've got x's here colored by their identity, not by their name. So at the start, there's an x in the outside the let, and then there's an x inside the let, which is a different x. So I guess another point about this is that say you're writing some tooling like VS Code or the language server, and you'd like to hover over a variable with your mouse and have all the variables which are that same variable highlighted or something like that. So with this, as this kind of like internal lowering pass available to call, we could provide that kind of experience.
4 minutes.
Yeah, OK. So we're running out of time. OK, so the last thing I'd like to show about this is the compiled expression. We're going to do this. So in this case, we could look at the provenance of, I won't show it, we're running out of time, but any of these statements in the linear IR, so this is like the tree structure of this expression has been removed here, any of these statements still carry full provenance information. So you could show the provenance tree of those. OK, I had a couple more examples here, but I don't have a lot of time left. So we might skip the macro one and go to the last slide, because I'm excited about this. So I'd like to do a demo, but I think I don't have time. So while we're doing all of this, we basically can't use the expr data structure. It's not sufficient to contain this information. So we've needed to invent a whole new set of data structures for carrying provenance. And while we're doing that, we may as well fix a bunch of other issues. So there's been long-standing issues with macros not being able to call other macros, macros not being able to emit code which has a macro call in it. And that's due to macro hygiene. There's a whole pile of subtle and rarely encountered bugs in macro expansions, the way that macro expansion produces global refs. So like whether it knows that the code that's been emitted by the macro, it figures out that code contains like variables from the module the macro was written in. And one of the big complaints people have about macros is that the ESC, the escape for macro hygiene, is very confusing. And I plan to delete it. And so, so maybe we have like 1 minute left. I might show the demo of that if I can. In fact, no, I'm going to like leave it time for questions.
Maybe we can take one question quickly over there.
Yeah, I think it's a short question. You said that those provenance trees can actually be like non-trivial trees, non-linear trees. I can't really imagine a situation where this would be the case. Can you quickly say something?
Yeah, neither could I initially. OK, so they can be trees when you have macro expansion. So with macro expansion, you have 2 locations at least in the user's source code which are relevant. There is, well, when a macro emits some code, that macro can arise from inside the macro like implementation, right? So that code has 2 sources of provenance. It has the place where that code, where the macro was called in the user's source code, the user of the macro, and then it has the location of, like, inside the macro definition. So there's 2 different places where that piece of syntax arose from. And then when you have macros calling macros, that can be like an arbitrary tree with having like multiple sources of provenance. Yeah, this has been one of the most confusing things that I've done in this project so far, like to figure out what to do.
Do you want to add anything?
No.
OK. We'll have to leave it there, but I know they'll be around, so you can ask them more questions.
Yep.
So let's thank again. Fantastic.